Hello, Adarsh. Adarsh. So,
Hi, how are you?
uh, I'm fine, thanks. And so, the show is all yours. Thank you.
Cool. Hello, everyone. Thanks for joining. Let me share my screen. All right. Hello, everyone. Thanks for joining my session. Hope you all are staying safe. My name is Adarsh Shah. I'm an independent consultant who works with various clients, helping them with engineering leadership, coaching, and hands-on architecture needs. You can find more info about me on my website. So today I'm going to talk about deploying machine learning models to production. What are the various challenges that you face that are machine learning specific and solutions that I've found useful using MLOps? First, let's talk about difference between traditional software engineering and machine learning. So as you can see here that traditional software development includes writing some program, providing some data, and then you get the results out of it. If there are changes in the program, if there are changes you need to make those changes in the logic of the program or in the data, and then you get different results. And in the machine learning world, you have two steps here. The first step, you actually provide the desired results that you want and the training data set. And I'll talk more about training a little later. But basically, you use the desired results and the training data and the training code to generate the program in the training step. And then use that program in the next step, which is the model serving phase, where you use that program, use live data in production, and then get the results, which sounds pretty similar to what a traditional software development does. Second stage, I'm talking about model serving. But as you can see, the program is actually generated in the training step. So even though they are fundamentally different, software development, traditional software development, and machine learning, most of the best practices that you can use for software development can be used in machine learning phase as well. Let's start by understanding a typical machine learning workflow. So as you can see, there are three different parts to it. First is data management. Second is experimentation, and then production deployment. So in the data management phase, you are looking at acquiring data, and data scientists spend a lot of time because data is really important, and having the right data and right amount of data is really important to get the training right and get your algorithm that was generated in the training phase right. And then you prepare for the data. So if you have to massage the data, make any changes, I can give you one example. In one of the projects we were getting images from the client, but the labels in the image were in a different language. So we had to do the translation before we could use it in the training phase. And then once you're done preparing the data, you go to the experimentation phase, where data scientists spend a lot of time developing the model. They use various algorithms, various model architectures, and then they also try different data sets, different version of data, and then they train the model. They train and see if it's meeting their expectations, if it's hitting their criteria, including various ways of percentage of acceptance criteria. Once they do that, they go to the production deployment phase, where the model is ready and is deployed in production, and it starts serving live traffic. Once that happens, you constantly keep on checking for accuracy of the model. Accuracy is pretty important because, as I mentioned, that the algorithm is generated during the training phase. If things change in production, so for example, you start supporting new products, or your environment in production changes a bit, you need to train the model again. So as you can see, there's an arrow going back for retraining or any code changes that you need to make. So all of that needs to happen, and you need to go back to the experimentation phase, and then you retrain the model and then deploy it again. I'll give an example here, which we'll use going forward. So one of the examples of things that we have looked at is identifying defects in assembly line. So let's say you're making mobile phones, and in the assembly line, you have a QA phase, quality assurance phase, where you want to make sure that the items are not defective, in this case, mobile phones. And you can create machine learning models that actually look at images of the mobile phones that are coming in from different angles, and then they look at any defects within that, so that a human doesn't have to do that, and we can automate those things, and humans can spend time doing more productive things, because this one is more repetitive and something that computers can handle easily. So here's a fun fact about model training, since we are talking about models. Have you ever helped train a model? Guess what? Everybody has. They just don't realize it. Have you seen captchas? Have you ever filled up forms while filling up forms on various websites to verify that you're a human? Have you filled up this captcha where you have two different words? This is basically Google using you to label their data. And labeling data means you are actually helping identify the image with actual words, and then they use that during the training phase to train the models. Similarly, if you have seen this, where you are actually identifying, let's say, street signs, it's actually used by Google to train their model for self-driving and other capabilities. So just something I wanted to share, a fun fact, which I knew last year. One of the known truths of the machine learning world is that it takes a lot longer to deploy machine learning models to production than to develop it. According to the paper, Hidden Technical Debt in Machine Learning Systems, only a small fraction of real-world machine learning systems are composed of ML code, as you can see it in the small black box in the middle. The required surrounding infrastructure and all the other supporting aspects, they're really vast and complex. So you need to focus a lot of time making those things right for your machine learning models to work in production. So now let's talk about some unique challenges that are machine learning specific than usually what you find in traditional software development. First one being data management. As I mentioned earlier, that data is pretty important for the training phase, and having the data right and the right amount of data is pretty important. So as you can see, usually you need large data sets, which is usually hundreds of gigabytes or even larger in size. So you have to keep that in mind when you are building those systems to deploy and train those models. Data location is another thing. You might have data in some cloud provider on an S3 bucket, let's say, or you have it on-prem location, or at some edge location. If you're working with retail clients, your data might actually be closer to where the store is. So you have to keep that in mind when you're building the system. Moving large amount of data across the wire is expensive and time consuming. So you might want to run your training or even model serving closer to where the data resides. And then security and compliance. Obviously, when you talk about data, you have to think about security and compliance. This is not necessarily machine learning specific challenge, but since data is of key and there's a lot of data involved in machine learning, these are important aspects. Next one being constant research and experimentation. As I mentioned, data scientists spend a lot of time experimenting. They try different data sets, different versions of data sets. They try different model architecture to see what works and fits their needs. They usually use Jupyter Notebook, which is one of the tools for experimentation and writing code. And while they are doing that, their focus is not code quality. Their focus is doing the research and experimentation and seeing what works for them and what doesn't. So the code quality during that phase is actually not as good. So you have to keep that in mind before you take that model and deploy to production, and any other code that's surrounding that. So yeah, next one being training process. This is unique to machine learning, and usually training takes time. Let me give you an example. Tesla's autopilot neural network, it takes about 70,000 GPU hours to train the full model. Now, it doesn't take 70,000 hours to train them. They just parallelize that with multiple GPUs. But still, you can still see the gravity and how long it takes to actually train it. I have had cases where it took hours, and some cases 2 to 3 days to train the full model. And we had to make sure that we support that in our platform. Reproducibility. You train with different data sets, change a few things. You should be able to reproduce the training process and then compare the differences so that you know which ones are better and which ones are not. So reproducibility of this step is really important. And you need to be able to track experiment. As I mentioned, that if you try with different data sets and different combinations, you want to be tracking those and making sure that you can go back to the previous experiments if you had to. And then retraining the models. If, let's say, the performance and accuracy of the model reduces, you should be able to train them again. There are specific infrastructure requirements for machine learning, especially GPU and high-density cores. GPU is graphics processing unit. What a CPU does is it works together with GPU to increase the throughput of data and the number of concurrent calculations within an application. So as I mentioned previously, that if it takes a lot longer to train the model, and even in cases, in some cases in production, when you're serving the model, it takes longer. So having GPU helps you run concurrent calculation and reduce that time. So GPUs were originally designed to create images for computer graphics and video game consoles. But since 2010s, GPUs can also be used to accelerate calculations involving massive amounts of data, which is exactly our use case in most machine learning use cases. And then elasticity. Since training needs to happen for a certain period of time, and then you don't need those resources, even inference, you might want to increase elasticity and support more traffic in certain cases. So having an option to bring provision and deprovision your infrastructure makes you it helps you reduce your cost, because especially if you're running in cloud, you're actually paying by the hour, and these GPU nodes are really expensive. So having that automation to provision and then deprovision once you're done your infrastructure really helps reduce cost. We always, whenever I look at a proposal and work with clients, I always look at this aspect really closely, because depending on what's the uptime and how much traffic, you might you should look at optimizing how much GPU you need in the cloud. And then edge devices, especially in computer vision, where you have a camera and where you are processing images. So in our case that we talked about for detecting defects in the assembly line, you usually have cameras, and that camera take images, and you want to process those right away. So there are devices by NVIDIA and other companies that have GPU support. So for example, NVIDIA Jetson Nano is one of the devices I have used in the past, which is like Raspberry Pi, but has GPU so that you can run machine learning workloads. So I've used that for model serving. So basically taking, there's a camera running, you take those images of items and then process it right there. So your NVIDIA Jetson Nano is attached to your camera. Testing. Now, obviously, in traditional software development, you should have testing as well. But there are some special tests that apply to machine learning. And I'm going to be talking about those. So data validation is one where in your data pipeline, and we looked at that in detail next, but you should be validating your data whenever you get, you might be getting data from different sources. So have a step where you're validating your data that it meets the schema and other requirements. Model bias and fairness, having these kind of tests and making sure that your model is fair and without bias, bias for race, gender, age, income groups, and those things. So make sure that those things are not, your model is biased and fair. It is very important to make sure that you're not discriminating against a certain group. And then model accuracy. So validating whether your model is accurate and not just during the training process or after the training process, but also when you're serving the model. So make sure that if anything changes, you go back and retrain the model and improve the accuracy. And the last but not the least is dependency hell. Now, this is something from my experience working with various libraries that you need to work with GPU and some of these hardwares. It is, believe me, I have spent a lot of time working with these, and certain dependencies only work with another dependency, certain version. CUDA being one. So CUDA is a library from NVIDIA that helps you parallelize some of this processing. And it is pain to work with. And there are other dependencies as well in that ecosystem that are painful. So keeping that in mind helps you build a solution that eases that pain. And then especially if you're working with edge devices, they usually run on ARM architecture, not x86, which is what we are used to. And the dependencies for ARM architecture are different than your x86. And there are ways you can do stuff like in Docker, you can actually build stuff for ARM architecture in your x86 machine. But you have to do work to do that and make it happen. So keeping that in mind and learning is really important. So yeah, here we talked about all the challenges that I've seen, and let's now talk about solutions. And well, this is one of the buzzwords where people use MLOps. What exactly is MLOps? It is nothing but applying the DevOps principles and practices that we have used in traditional software to machine learning. But since, as I mentioned, that some challenges are unique to machine learning, MLOps helps you solve those challenges. So as we talk about people, process, and technology in DevOps for traditional software, same thing applies here. But what is different is what we'll talk about next in terms of solution. So there are certain roles that are different. You look at ML researchers who's focused on doing research and experimentation, and they don't focus on writing production quality code, but they focus on getting the research and experimentation side of things right. You have an ML engineer who's basically in between machine learning researchers and software development. So they have some machine learning knowledge, but also good software development practice knowledge, where they help bridge the gap and productionize the code. And then data engineer, who's mainly focused on getting the data right and writing pipelines and ETL and other things to get data for testing and even inference. And then I'm an ops engineer. Now, I was going to write DevOps engineer, but since we're talking about ML, I just call it MLOps engineer. You need to understand the DevOps practices and principles, but also have some understanding of machine learning and the challenges that it brings. So yeah, like those are the roles. And then let's talk about some team structure considerations. So as in traditional software development, cross-functional teams work best, where you have a team that includes your researcher, your data engineer, your machine learning engineer, even your DevOps or MLOps folks and software engineer, bringing them all together and building a cross-functional team that is focused on building the product right, and having all the different components is always great. The challenges that we talked about support for constant research and experimentation, and then the code quality and things that we talked about. If the team is cross-functional, there is better collaboration and they have common goals and incentives. Even the infrastructure requirements are unique and challenging. So having someone who understands infrastructure in your team also helps. So I would recommend building a cross-functional team if you're working with machine learning projects. But in cases where you can't have that and you need to have a separate data science team, which is okay as well, but you need to make sure that you promote collaboration between teams. I have seen places where the data science team is doing their own thing and don't collaborate closely with other teams. And that causes issues because they're working on things that the platform can't support, and there's not enough collaboration. So even the incentives for various teams, including data science, should be in a way where they go towards same incentives towards the end. And then this is basically a platform engineering team, but focused on machine learning. So as I said, that if you have GPU and other needs, which most of the ML projects have, you might want to have a focus team that builds this platform. And I'll talk about it in a bit about that as well. So here's a typical data pipeline. You have a data source, you validate the data, the tests that I talked about previously. Then you acquire the data, and then you prepare the data before it can be used for testing. And then you apply that, and you might have different sources. You might be getting from different cloud providers, open source data that's out there, open data, and other things. So having a pipeline like this and automation that helps you build the training data set is really important. And then that becomes an input in your training process. Now let's look at the training pipeline, which is another crucial and a lot of various challenges that we talked about, we look at addressing here. So first is, let's say you're a data scientist or someone who wants to schedule a training, uses a Jupyter notebook or a UI command to schedule the training. You have your training code that's coming from your repo. You do your typical CI with that code as well. And then you provision a training environment. As you can see on the right, you have infra provisioning automation with GPU support. What I have used in the past is I've used Kubeflow, and we'll talk about that next, which is a platform that helps you get and solve some of these challenges. So yes, having that automation to provision, and then once we are done, deprovision is important to save cost, but also other aspects. And then you provide some pre-trained weights, which are basically ways for you to get started with the training process. And then the training data set that was created in the data pipeline stage goes as an input as well. You provide monitoring, logging, and alerting. As I mentioned previously, that training takes time. And if things go wrong, you should get notified right away so that you can resolve them and continue training or restart them based on your use case. So having logging also helps, and alerting. So having all of these things so that you're not stuck there. In our cases, we used to start the training, go home, come, and then when we come next day, we might have some good progress. But if something fails, we used to notify. So because you don't want to wait till later to find out issues. So yeah, like it's really crucial to have proper monitoring, logging, and alerting at this stage. And you validate whether the training actually worked and if the accuracy is good or not. And then if that works, run bias and fairness testing. Having automation here really helps. And then build and version your model so that you can push it to Docker if you feel like, which helps you have versioning and other aspects. And then you push your image to Artifactory. So this is a typical training pipeline, and we kind of touched some of these various aspects of challenges that we had, including maybe packaging in your Docker container so that you don't have the dependency hell and you know which versions you're using. Okay, so next stage is deployment pipeline. So deployment pipeline, and this is a use case that I have used. You don't have to use GitOps, but we used GitOps, which works pretty well with Kubeflow, which is what we have used in the past. But you push to master in your GitHub, let's say, it triggers a build with Argo, and it deploys your model in production. You basically pull the image from artifact repository that you pushed in the previous stage. And again, provisioning your infrastructure automatically helps here, and you might want GPU support. Again, monitoring, logging, alerting, having all of those aspects there. And then periodically evaluate your model accuracy. See if things are going down, if the accuracy is going down, and if you need to train the model again. So that's the typical deployment pipeline. I haven't mentioned a lot of usual things like test automations that are also common to software development, traditional software development, and talked only about ML specific stuff. So let's quickly talk about, I know we are running out of time, but I'll take 30 seconds to talk about various platforms that are available. So the ones on the top, MLflow, Kubeflow, and Apache Airflow are agnostic, and you need to manage those platforms. And then the ones at the bottom are what cloud providers provide, and they're managed. So here's Kubeflow, which is what most of my experience is. And as you can see, it supports things like pipelines, experiments, tracking experiments, serving the models, and serving PyTorch model and TensorFlow models, and then model training and all of these aspects, working with Jupyter notebooks and providing a Jupyter lab. So yeah, like a lot of those things are supported in Kubeflow, but also having good practices in terms of automation, team structures, and people process part of it is really important. Okay, here's the summary. I'm not going to go through each one, but that's what we talked about. And that's all. That's my talk. Thanks for listening, and happy to take any questions. But again, my name is Adarsh Shah. Thank you.
Hello, Adarsh. So we have kind of questions.
Yeah.
I'll put them on screen so it's better for you to understand my English.
Sounds good.
So we have two questions from the QA section of the website. They are both from Wallet. So the first one is, how about Devops from NVIDIA and Red Hat Data Hub? Do you see any community support and improved workflows utilizing them? If not, what do you recommend?
Yes, there is good community support. I have definitely used a lot of NVIDIA forums, and NVIDIA folks are pretty helpful there. The support for some things like Docker and containerizing things with especially edge devices are challenges. So I mentioned NVIDIA Jetson Nano when I was talking about edge devices. And it's very painful to make Docker or other things work there. So I've used community there, and they are actually working on improving those things. So yeah, I don't know much about Red Hat Data Hub. I haven't used it, but NVIDIA support and community forums are definitely helpful. And I have used and even contributed a bit along the way. Hope that answers your question.
To me, at least, it answered. Maybe Wallet can talk to you later at Slack. So the next question from here is, needs to support the ops and infrastructure of MLDL, which I think it's machine learning and deep learning solutions to users. How can I enhance my skills? What if infrastructure and ops resources do you recommend?
Yeah, good question. I went through that journey. And that is actually one of the things about this talk. Understanding those challenges that I mentioned, I can share some of the resources I've used on Slack, links to it. But basically, understanding those challenges, I am in our use case, especially, we had a need to run that in different environments, cloud versus on-prem, because if the data is on-prem, we had to run those things there. So I've used tools like Kubeflow, but getting understanding of how GPU works, parallelization, and some of the challenges that I talked about are something that if you focus on and learn will help you understand what to do when working with machine learning, deep learning. But yeah, let me share some of the resources that I've used on Slack. It'll be easier.
Okay. So thank you, Adarsh, for being here with us. Do you have anything to say?
No, that's all. I had fun giving the talk, and thanks everyone for listening, and thank you to you for introduction and helping with questions. All right. Any other questions? Let me know on Slack. Bye.
Okay, thank you.
Thanks. Bye.